Two important results in Fourier analysis are Parseval's theorem and Dirichlet's theorem. As a side note, all of Fourier analysis theorems were not proved by Fourier. They were discovered by Fourier, but actually proved by Dirichlet. Dirichlet gave formal proofs of every single Fourier theorem there is. So I doubt if even Fourier wrote something like this in his lifetime, although he must have surely thought that. As a matter of fact, the manuscripts that Fourier sent to the Paris Society on his initial investigations into Fourier analysis were rejected by Lagrange as being too sloppy. And it's not until many years later, many decades later, that Dirichlet cleaned up the entire subject. So if you see anything that looks rigorous, it's due to Dirichlet and other people around that time, like Parseval. So the two theorems you have here, first of all, let me tell you what Parseval's theorem is. So you write the Fourier series in either the sine-cosine form or in the exponential form on this interval minus pi to pi. On other intervals, you just modify it according to the previous videos. Parseval's theorem is the statement about the average value of a function of the same function squared. Now the regular definition of an average is the following, the one that you know from calculus. So the average value of the function squared is over the interval because of length of the interval is 2 pi, you write 1 over 2 pi, and you find the actual value of the function, absolute value of f of x squared dx. So that's the traditional definition of the average. Well, you can calculate the average also by examining the coefficients of the Fourier series. So Parseval's theorem gives you the answer. It's a0 over 2 squared plus 1/2 the sum of all the an squareds and all the bn squareds. The Parseval's theorem is extremely useful, as we'll see later in this video, to get estimates, really quickly converging estimates of something like pi. Now, Dirichlet's theorem is very long and very complicated, but the basic thing I want you to take away from it, the full statement is given in my notes, is that if you have a jump discontinuity, the Fourier series actually converges to the midpoint of the jump. So as a great illustration of both these, let's take the function called the bump function. It turns out to be one of the most important functions to study in Fourier analysis. Right now we'll assume the bump function to be periodic. In other words, we'll assume that it keeps going like that, bumpy all along the real number line. But later on we'll take the bump function as being just a bump later in this week, and we'll find its Fourier transform, or the integral transform of the bump function. So the bump function is defined as follows. F of x is equal to 1. It's like an on-off switch if minus x is less than x less than 1, and outside it is 0. So for, let's say, -2 less than x less than -1, and for 1 less than x less than 2. So on either side of the on-off switch, it's 1, it's 0. So the length of the interval here is -2. So because if you notice, we have everything defined from -2 to +2. So let's draw a rough sketch of the bump function, which I'll do here. It's best to sketch it first in the principal domain indicated. So I have like that, -1, +1, 0, and then from 1 to 2 there's nothing. This function is not defined because there's less than or equal to sign is needed to be defined. So it's got holes in both those places. Observe that. There also it's got a hole. So it's full of holes. Now it turns out that Dirichlet's theorem is so general, your actual function need not have any graph at all. You can have a function that's made up of complete holes and nothing else, like a fractal. And Dirichlet's theorem is still valid. You can see how important Dirichlet is to the history of mathematical analysis. And various counterexamples in analysis textbooks, in good analysis textbooks like Rudin, you will find the name Dirichlet all over the place. So Dirichlet even applied the Fourier theorem to a class of functions called Dirichlet functions, where the function is defined to be 1 at all the rational points and 0 at all the irrational points. Can you imagine that? You can't even draw that thing. So let's talk about the various basic things we can do with this function. Well, you can certainly find the a-naughts, an, and bn. So let's proceed to do that. A-naught using the modified definitions with the interval L. So negative L to L is negative 2 to 2 here. So that's minus L to L. F of x dx, that's our definition of a-naught. Let's calculate that. It's 1 over 2 integral. Now it's 0 between 2 here and it's 0 there, so I won't integrate from minus 2 to 2. Instead, I'll integrate just from minus 1 to 1 because that's the only place where it's not 0. F of x is just 1, so it's 1 times dx. And that's just half times x between the limits of minus 1 and 1, which is half times 2, or 1. Similarly, an is 1 over L integral minus L to L f of x cosine. Now normally I would have written nx, but because its interval is negative L to L, remember from the previous video, I have to previous week's video I should say, I should write this as n pi x over L dx. So once again, L is 2, and I'll integrate just from minus 1 to 1 of cosine n pi x over 2, because that's what L is, dx. Now if you integrate this, cosine of ax dx is just 1 over a sine of ax. So a now is n pi over 2. So 1 over a means 2 over n pi. And sine of ax, so that's n pi x over 2 between the limits minus 1 and 1. And that gives me 1 over n pi times sine of n pi over 2 minus the sine of negative n pi over 2. Well, the sine of negative theta is the same as negative sine theta, so the two negatives will cancel out, and I end up getting 2 over n pi sine n pi over 2. Now there are two cases. You have to investigate the n equals even and n equals odd case. So if n is even, you're going to get things like, the best way to write n equal to even is n equals 2m, because all even numbers can be written as 2 times m, where m is an integer. So let's investigate that case. That gives me, so sine n pi over 2 will become sine of 2m pi over 2, which is sine of m pi, and that's 0. So for even values of n, this makes no contribution whatsoever. For odd values, let's see what happens. Odd numbers can be represented as 2m plus 1 for integer m. So I can write sine of n pi over 2 as sine of 2m plus 1 pi over 2. Taking the 2 inside, I get sine of m plus a half pi. And here I can use my sine a plus b formula. So I get sine m pi cosine pi by 2 plus cosine m pi sine pi by 2. Well, cosine pi by 2 is 0, so I just get the contribution from here. The cosine m pi is negative 1 to the power m, because for m that is even, it's going to be 1. For m that's odd, it's going to be minus 1. And sine pi over 2 is just 1. So I get that answer. The bn coefficients are going to be 0, because the function is an even function. Bn will make a contribution only if the function is an odd function, because Bn has got integral of f of x sine. Sine is an odd function, and if f is even function, the product of an even function and an odd function is again an odd function, and so when you integrate it between symmetric limits, you will get 0 answers. You can verify that. It's not worth wasting time in this video to verify that. So our Fourier coefficients are basically a of 2m plus 1 is equal to, I'm copying the basic answer here from here. I'll put n equals 2m plus 1. So I get 2 over 2m plus 1 times pi negative 1 to the power m. So that's our answer. We have finished the problem of writing it as a Fourier series. Well, not quite. We have to write the final answer as a infinite sum. So let's do that. F of x equals a naught over 2. So that gives me 1/2 plus the sum from m equals 0 to infinity. Now remember, even though we are looking at n specific values of n, which is odd numbers, this once you write n as 2m plus 1, m goes from 0 to infinity. So you don't restrict m in any way. So that becomes 2 over 2m plus 1 times pi times negative 1 to the power m cosine m plus 1/2 pi x. On the face of it, I just wanted to appreciate how remarkable this statement is. You're saying that something that looks bumpy like that can actually be written as an infinite sum of sines and cosines, in this case just cosines. So that itself is quite incredible. Now just make sure that Dirichlet's theorem is satisfied. Dirichlet's theorem says when you have things like jump continuity, for example at 1 or -1, you will get the midpoint value. The midpoint value is going to be exactly half. So let's verify that we get that. Let's take +1. At +1, I'm going to get f of 1 equals half plus Dirichlet's theorem tells you what f of 1 is. F of 1 is half. So I'm going to get, so that's f of half plus, I'll get cosine m plus half times pi. Now cosine m plus half times pi, let's just work that out. So typical term is going to be cosine m plus half times pi. I won't write all this stuff because x is equal to 1. When you expand this out in cosine a plus b terms, I'm going to get cosine m pi, cosine pi over 2, which is 0, minus sine m pi, sine pi over 2. That's also 0 because sine of m pi is always 0. So this thing is exactly 0, and so Dirichlet's theorem is satisfied. It exactly comes in the midpoint. Now let's use a specific value of f and get the value. For example, what is f of 0? Let's try what f of 0 is. If I put 0 here, the function at 0 is clearly 1. So I get 1 equals half plus an infinite sum from m equals 0 to infinity 2 over 2m plus 1 times pi negative 1 to the power m cosine of 0, which is 1. So I won't even write that. Now if I take the 2 over pi outside, I'm going to get, this tells me 1 plus half. So I'll take the half to the other side. This tells me half is equal to 2 over pi integral m equals 0 to infinity negative 1 to the power m over 2m plus 1. That's an amazing equation because it tells you what a possible expansion of pi is. If I take, and this is one of the earliest expansions of pi ever discovered. If you take pi to the other side and 2 down, I get pi over 4 is equal to, now let's try to expand this. For m equals 0, I'll just get 1. And for m equals 1, I'm going to get 3 down here, but that's going to be a negative sign. So 1/3 plus 1/5 minus 1/7. And if you try this on the computer, you'll find that it converges incredibly slowly. Just to get the first 3 decimal places, you have to go several hundred terms. Now, how do you speed things up a little? And the answer to that is using Parseval's theorem. Parseval's theorem goes as squares of everything, so it can be incredibly sped up. So let's start by finding the average of f squared first. The average of f squared is going to be using the definition of the average I wrote here. It's just the integral from 1 over 2 pi. That would be how you would do it. But since this is going to be 1 over 2L, and L is 2, so that's 1 over 4, 1 squared dx from -1 to 1, and that's just 1/2. Okay, so that's one way of finding out the average. The other way of finding out the average squared is this one, the right hand side of Parseval's theorem. So let's do that. So I'm getting by Parseval's theorem, by PT, I'll get the following. The average value of f squared is a0 over 2 squared plus 1/2 the sum of an squareds, n equals 1 to infinity. So that's what, because there's no bn terms. So I've already calculated the average the usual way, so I get 1/2 on the left side. On the right side, a0 is 1, remember. So 1 over 2 squared is 1/4 plus 1/2 again. Now when I square the an coefficients, I'm going to square this thing here. So it's going to be the sum from m equals 0 to infinity, 4 over that thing squared. 4 over pi squared, negative 1 to the power 2m, because when you square negative 1 to the power m, you get negative 1 to the power 2m, over 2m plus 1 squared. Let's try to parse this out. First of all, quarter minus half is a quarter, and then if I take the, and then there's another half here, so let me do this. So this gives me 1/4 equals 2 and 4 cancel out, 2 over pi squared, the sum from m equals 0 to infinity, 1 over 2m plus 1 squared. That's because negative 1 to the power 2m is always plus 1. This gives us an even faster converging series for pi. Pi squared over 8 is 1 plus 1 over 3 squared plus 1 over 5 squared plus 1 over 7 squared. It's the same terms as we had in the original series, except all these things are squared. And this converges incredibly fast, as you can verify using a computer.